Thank you. Courtney and I will be talking about the mineral potential model in the Quamby region today. My name is Matthew Greenwood, and I'm the manager of the Regional Populations Group at the Geological Survey of Queensland. And Courtney, do you introduce yourself?
Yeah, I'm Courteney Dhnaram. I'm in the Mineral Systems team in Minerals Geoscience.
And this is a bit of a change of pace to a more of a multidisciplinary approach that use techniques from 3D geological modelling, geophysical inversions, and weights of evidence to create a common Earth mineral potential model. So I guess the first question we need to ask about why we're talking about Quamby is why we're talking about Quamby now. This is a project we finished 7 years ago. And I think while it is an older project, it's a really good example of a multidisciplinary geoscience approach taken to bring together lots of different geoscience data sets into a unified common Earth model and use them to test our understanding of the mineral systems present in the area. One of the major drivers for this project and this kind of mineral potential modelling was to highlight the wealth contained in the open file geophysical data sets available from the GSQ. In this project, only open file data sets were used. No new data apart from some petrophysical samples was collected as part of this work. And I think this work really highlights the value of these legacy data sets for exploration. And importantly, and this is probably jumping right to the conclusions at the end, while the project results in a model that we can spin around in 3D and has red areas and blue areas, the real value that we gain through this type of approach is the understanding about the relationships between the different data sets and the mineral systems understanding gained through the work rather than the pretty sort of outcome model at the end. So I guess more in the why here, why we selected this area. We focused on the Quamby area because it was north of the currently existing Mount Dore model, which was done as part of the 2011 Northwest Queensland Mineral Energy Province report with Mirror Geoscience. And at the time of this report, Courtney and I were both members of the Greenfield Prospectivity Unit, which was looking at ways to best promote exploration undercover. This area is quite a prospective area in terms of the mineral occurrences in the area, including Ernest Henry, Duga River, Eva, that George is going to talk about shortly, Rocklands. And it's covered by a fairly shallow cover veneer over a fairly prospective area. And so it was trying to promote that exploration to drive undercover. I'm going to lead the talk off about mainly around the modelling work that was done and the geophysical work, and then Courtney's going to pick up with the mineral systems presentation a bit later on. The project area is 95 by 80 kilometres wide, located north of Cloncurry, includes lots of major operating mines as well as significant prospects. As I said before, sediments cover about 70% of this area. And so, however, most of that area is only about 200 metres maximum of thickness of cover. Prospects for multiple styles of mineralisation, but as you can see, all the known mineralisation, or majority of the known mineralisation, is constrained into the central belt of where there's outcropping geology. But the same geology continues out into the covered areas. And so this was trying to take the understanding we have in those outcropping areas and push it undercover. A bit about some of the input data sets. As I talked about, this is all open file data publicly available, including the geology mapping and MinOc mapping, gravity data, magnetic data, faults and horizons from our Northwest Queensland 3D model, deep seismic data, cross sections that was done as part of the Northwest Queensland province model, and also MT data. And also, just to point out, since this model has been completed, we have the East Isa survey, which Andrea was just talking about, the East Isa AEM survey. We have the Cloncurry MT survey, which sits within this area. And also we have 3 new 100-metre line space mag surveys that's been done in this area. So there's lots of new data in this area, even though it was quite a data-rich environment to start with. A bit about the modelling flow. I'm going to rush through a bit about this because I really want to focus on the outcomes that came out of that. So we started with our geological map. We built some cross sections from these, east-west and north-south cross sections. So I'm just showing some of those east-west cross sections there. They were built from our particular field data, a lot of our other data sets in the area. From there, we created a 3D fault model in Skua or GoCAD from all that available information. And then we created our 3D lithological surfaces. So these are surfaces representing the base of our major geological lithological packages. that was built in GoCAD Skewer, again, built from most of our input data sets that were available at the time. And finally, we took this 3D surface model, which is a vector model, and discretized it into a 3D voxel model to facilitate geophysical inversions and our weights of events modeling. So you can see we've gone from a surficial model there into a volumetric model using cells. Or if you think about pixels, these are now voxels, so they're three-dimensional pixels, which we can populate with physical properties. So now I have the first of my videos, which I hope is working, where you can see our surficial model there. And I'm going to slice into the surface model and then pull back through. And you can see we're trying to maintain that lithological contrast across there. These are the broad lithological packages we're capturing here rather than every particular unit mapped in the area. And then I'm going to convert that now into a voxel model. So now we have volumes that we can populate with physical properties. So the next step we took with these was with potential field inversions. So from our discretized voxel model, we then populated those with physical properties. So as part of fieldwork, we collected samples to get mag sus values or density values for those rock units to populate those into our Common Earth model. The first step we did was a set of homogeneous property inversions on the data. So this is looking where we're giving each unit a mag sus value or a density value, and then set the inversion to fit the data, the observed data, and each unit is permitted to vary within a user set range to optimize that starting model. Inversion, like a lot of the modeling processes, isn't a single step process, but is an iterative process. So it's doing an inversion and then it's going back to refine the model geometry or understand that there are areas that don't fit and play with the geometry or try to understand why it isn't working. After we did the homogeneous property inversions, then we moved on to heterogeneous inversions. And here we allow each cell within each unit to vary within that set range. Now we're getting understanding about the variance of those physical properties within those units as well as across the model space. As I said at the top of the presentation, the final model might be pretty, but the questions asked about it and as part of the process can be far more valuable. So while we're seeking to best fit the geophysics here, the local anomalies where we can't fit the observed geophysics is probably the most interesting bit. Now this might be alteration, it might be unmapped units, or intrusives, it might be concentration of dense or magnetic units in particular areas. And so I'll step in to talk a bit more about the inversions itself. So here we have our final 3D density model, results of several generations of iterative inversions, constrained by the geological model and the set of density inversions. As I said, this is not the first inversion we came out. This is a process of multiple sets of inversion. And this is the final density model. So red where it's higher density and blue being lower density. But the next step we took here, and I think this was an important step, is we then looked at each of the units across the model and worked out the unit mean, and then each cell was given a standard deviation from its unit mean. And so what we're looking at there is how different compared to the average of that unit or the mean of that unit, each cell within the model is. And I think this is important to look at the standard deviation because within some units, a 1 gram per cc variation may not be very significant. For example, one of the units used in this modeling was the Corella Formation. Now, the Corella Formation has multiple lithologies grouped within a larger formation. So a 0.1 grams per cc variation may not be so significant within the Corella. However, in a more homogeneous unit like a granite, for example, a 0.1 gram per cc variance is far more significant. And so we did that for the density model. And we also did that for our 3D mag susceptibility model. We did these inversions using VPMG to do both the homogeneous and heterogeneous unit inversions. So we have our final 3D mag sus unit. Red is high mag sus, blue is low mag sus, and then our standard deviation from the unit mean within those across the model space. So I'm now going to pass over to Courteney to talk a bit more about the potential field modeling as the next step here. And do you want to request to control the computer as well, Courteney? And you're muted.
I definitely am muted. So excellent. So just following on from the sort of work that we started to do, putting together the geological model and starting to do the geophysical inversions, I'm just going to preface this by saying I'm not a geophysicist at all. I used to think of myself as an honorary geophysicist, a part of the Greenfields Prospectivity Unit. But it was one of the first times where really we started to work together across our units within a team and try to have a multidisciplinary approach to these sorts of problems. So why mineral potential modelling? Well, some of the questions that came out of the earlier work that we did with the Mirror Mount Dore model and some of the ideas that were coming out of the PMDCRC work, as well as the work by GA, Dave Houston's work looking at the uranium and also the copper deposits in North Queensland, was trying to find a way to test our current knowledge on IOCGs or structurally controlled or hosted copper deposits. And we're focusing on both copper only and copper gold deposits in the area. Now, while we know there are a lot of other variations on the theme, and also silver lead zinc deposits like Dugald River, we took the approach that these deposits were part of the same mineral system. But honestly, it was a big question at the time. And now 7 years on, we're finally starting to get this sort of data to be able to differentiate things. One of the thoughts were do the same criteria that we have set for typical IOCG deposits, capture the range of known deposits in the area, and also what can we learn from modelling in 3D space about how we thought the tectonic domains or structural controls had on mineralisation. It didn't work, Matt. It didn't do anything. Thanks. So 5 questions, hopefully a lot of you are familiar with, and particularly turned into 6 questions by Dave Houston and the team at GA from 2010, was really trying to look at ways to go from source and pathways and fluids and having deposition, and then also the later post-depositional processes having on metal accumulations. So with these questions in mind, trying to understand what the fundamental controls were on copper and copper gold deposits in the area. I'll just do this, Matt, for slide changing. Sweet. The logic was adapted as part of the Northwest Queensland Mineral and Energy Report that came out in 2011. And essentially, we took a lot of the ideas, i.e. on a continental scale, you need a passive margin or you need a backup basin for these sorts of deposits. And we tried to create mappable or measurable characteristics that could be tested. Now, the focus was on the copper gold deposits, and because of the scale of the Quamby project, we were really looking from a district to camp scale, with a bit of sort of looking at terrain scale. But of course, if you were looking at all of Northwest Queensland or all of Mount Isa, you'd be focusing on continental and terrain scales. And then another example of the table, it's okay if it's a lot of words in there, but essentially it's looking at the ingredients, the processes, and what is important. What are the main things we need to capture? So part of the logic was, how can we turn these ideas into characteristics that we can input into our 3D model? So with weights of evidence targeting, essentially, I'm not going to get too technical here, but essentially it's an evaluation of the spatial relationships between known mineral occurrences. So that's our training data. So we picked a number of the major deposits across the area and their relationships with other spatial data sets. So these are evidential properties or our exploration criteria defined by the previous research, and they're turned into mineral potential probabilities. Then we had these probabilities, they're represented within our common earth model, which is the model that Matt just showed you, and as continuous or discrete variables. And then we used the GoCAD targeting workflow, which was a plugin to assess the correlation of these properties with our training data sets. So the weights, so positive and negative weights, were assigned from correlation between training cells and the evidential properties. So it was really important to try and work out what the cutoff value were between these values and convert them to binary properties so we can actually get a range of how far away from these particular properties it affects it. So contrast is defined by the difference between W plus, W minus, and the higher the contrast, the greater the discrimination. So on the right-hand side of my slide, you can see we have distance to crustal scale faults, also distance to granite. And then down the bottom, there's a curve, and the contrast is defined the highest 300 meters. So therefore, the values between 0 and 300 meters are defined as favorable. And as you can see, that then defines the areas of highest prospectivity. So we took these ideas and these properties, and we did modeling on just the top 2.5 kilometers of the model. Now, while the actual model goes down a lot deeper, and you can push a lot of data sets to the end of the earth, a lot of the data sets we were working with were superficial. We didn't incorporate a lot of downhole geochemistry. For example, we just used surface geochemistry data sets, so it wasn't fair to extend these too far down, and also who's really looking that far down at the moment. There was a lot of different exploration criteria, contrast and cutoff values across the geological domains due to different mineralization styles within the bigger mineral system, expected targets, and also depth of cover. So part of the learnings as we were doing this work was the idea was to run weights of evidence across the entire Quamby area, but we learned there was just too many differences between the area that was outcropping, so essentially predominantly the Mary Kathleen to the west of the model, while the Constantin was mostly undercover, so we didn't use all the same data sets across the whole area. We tested 23 evidential properties, including combination variations of inverted density, magnetic susceptibility, variation from mean and median of different units. Some of the things that we had seen to the Mount Dore model to the south, including things that Matt had mentioned earlier, looking at rheological contrast between particular units, funnily enough, actually weren't that important in the Quamby area. Just didn't seem to be as big a control in the area. Same with structural complexity, which we saw in the Mount Dore area, had a higher contrast and seemed to be more important control and mineralization didn't seem to have the same effect here. So you can see that surface geochemistry, copper gold, fault curvature, density deviations, distance to Williams granites, distance to faults all seem to be quite high. So this is the Constantin Domain. This is the main area that's in the center of the Quamby project. It's predominantly undercover. We were just looking at copper gold mineral systems in the area. The most important exploration criteria that came out were geochemical anomalies, geophysical anomalies, proximity to faults, because a lot of the faults in the model are quite major faults, and also uranium anomalies. And as you can see, these are different parts of the inputs. Here's an example of a horizontal slice at 100 meter, which is a crop that's about 100 meters cover. The red dots are known mineral occurrences, and then as I go slightly deeper, and this is about -100 meters, you can see that between the two, things are slightly changing. So along the far right hand, which is along the Mount Margaret fault zone, you can see it's starting to get higher, and there seems to be some more targets along there now. Right. Here's a sweet model, hopefully. It's just showing the same area with the mineral occurrences. We're spinning now, and we're going to start going down from essentially the surface, going down to show you the different areas. You can see up in the far eastern corner, northeastern corner, there's some anomalies underneath Cormorant, and then also along the major faults splitting the domain between Mary Kathleen and Constantin. And, oh yeah, we're going to do some sweet zooming in. That's good. This video was a slight surprise to me, so that's cool. And here is the same image with all the named occurrences, because you can stare at geophysical images all you like and models, but it does, unless you have an idea of where you are. So the Great Australia to the bottom area is just near Cloncurry, for example, and then you can see Ernest Henry. So one of the nice things about the results from this modelling is that it picks up the nice trend, sort of northeast trend that you see at Ernest Henry on a camp scale, but also on a district scale, essentially all the other anomalies that were picked out initially with the drilling for Ernest Henry. It also picks up some really interesting areas in the middle of the area with no known training sets. And as far as I know, not a lot of drilling has been done in there. So it's quite a very interesting anomaly for further work. Just going through the Kathleen domain, this is to the far western side of the project. We were looking at both copper only and copper gold mineralization. Very similar exploration criteria came up as used for Constantine. One of the only difference was potassium anomaly was quiet, and there was different strengths of association between these exploration criteria as seen in Constantine. But saying that, there is a lot less variation in 3D than in the Constantine domain, and I suspect part of that is because we still don't have a fully good idea about all the geology at depth with solid geology without having, drilling every 100 meters to map it out. So here's another image of what it looks like. There's the main faults coming through, and you can see most of those deposits are within the EVA project and along the Roseby copper belt. So yes, excellent. So it's the same image, just going down, showing you as we step down. I think there are 100-meter slices that you still see a lot of the red, which is the higher prospectivity areas as you go deeper in the area. Towards the major fault splitting the domains, there's a slight anomalism, but there wasn't anything, we didn't have any training data there, whether that affected how it was going. And as you can see, here's Queen Sally to native companion along the Roseby area, and then two of the smaller Emu and Gem areas. There's a link down the bottom for anybody who's interested in having a read of the Quamby report, and then also a link to the data package. So what did we learn? Hopefully Matt's going to jump in soon as well. Scale is important. Going into this, we had a lot of ideas that maybe were at a district to sort of like a bigger scale that weren't necessarily able to be captured in this model. Equally, we had things that we knew about second order and third order faults that had a control and mineralization, but also couldn't be captured because we use such a generalized geological model. Yep, good.
I guess some other learnings, I guess the common earth model approach, allowing to bring all the data for an area and being evaluated in a single system, really allows you to interrogate those data sets and view them in 3D together. And as I said before, I think sometimes the questions that you find from bringing all these data sets in can be more important than the final model result that you get out. These models are a point in time snapshot of the work being done. We can always incorporate new data and new ideas and new models into it and assess new criteria that we might be looking at. And I think this is evaluating to our large set of pre-competitive data available to explorers from the GSQ. Just to focus a little bit further on something similar to this work, some work undertaken recently by CSR Minerals and Data 61 in conjunction with GSQ was looking at using some machine learning techniques really across a disparate set, a large set of our geoscience data, and was really showcasing a couple of things about in that data. One of the main ones I want to talk about here was a comparison between this weights of evidence model in Quamby, using the same data, using a machine learning logistical regression technique, and then seeing what comes out of that. But in that report, there was geological classifications done using random forest, interpreted geological anomalism using support vector machine techniques, as well as some geochemistry modeling, which using a combination technique, mainly including random forest. So just on that, using the same color stretch, this is our weights evidence output from the Quamby model, with the training points in white, really hard to see in some of these models, versus the logistic regressor model for the Constantin domain. So I think both of these outcomes are quite valuable, and the logistic regression probably delivers a more discrete targeting and correctly identifies the location along these structured corridors better. However, the failings of some of these logistic regressions is that it really needs a lot more training data to work on these problems much more effectively. Similarly with the weights evidence modeling, one of the important tenets of it is that all your inputs are conditionally independent, and we know that in geoscience that we don't have conditionally independent inputs. So I think it's just another way of looking at this data and seeing what we can extract out of it. That report and the output data is published on QX Reports as well, and there's a link down the bottom there, and in the chat box, Courtney and I will throw the links for both the Quamby report and the the Data 61 data-driven mineral systems approach work as well. And just to the right there, some of the other outputs of that model. You can see some of the geological classifications, the granite classification model done as well. But as I know we're all over time, that's it for us, and we're happy to answer any questions that come up in the chat box.